All right, so continuing from that point that we left off in the last video, we're going to now analyze the same function and try and approximate the area underneath it using trapezoids. So if we're able to sketch that same function and this time draw trapezoids, 3 trapezoids that are on this interval in between -4 and 2, we can actually see that the trapezoids are going to line up perfectly with this linear function, and the area underneath it is going to be the exact area. As the function gets curvier, the trapezoidal method is no longer the exact area, it's just the closest approximation. But with linear functions, trapezoids are going to give us the actual area. So we still have subintervals of length of 2, that hasn't changed. We're using 3 trapezoids on this interval, so each of them have a subinterval length of 2. So our subinterval values are going to be the same. What we need to do is find the area of each trapezoid, and we're going to use our left and right endpoints on each interval. So if I plug in the left endpoint here and evaluate the function, that is the height of this base 1. If I evaluate the right endpoint on my interval at -2 and I evaluate it in my function, that is the length of my second base, or base 2. So we're evaluating the left endpoint of the function and evaluate the right endpoint with the function, and those are your base lengths. We're going to add up our base lengths, divide by 2, and multiply by this width, or the length of the subinterval, to get the area of the trapezoid. So evaluating the function at -4, plug in -4 into my function. So the opposite of -4 is 4, plus 4 is 8, and that is the height of the left side of this trapezoid, or the base, first base. Evaluate the function at -2, so plug -2 into your function. Opposite of -2 is +2, 2 plus 4 is 6, so the length of this base, or the height of the function at that point, is 6. So I'm going to take those two values, 8 and 6, add them together and divide by 2. But since I'm multiplying by 2, I can actually just simplify that and say it's 8 plus 6. But sometimes that subinterval length is not 2, so don't do that every time. If we're dividing by 2 and multiplying by 2, we can simplify that operation only when the subinterval length is 2. So if your subinterval length is different, don't just take this shortcut. But 8 plus 6 divided by 2 times 2 is 14. Let's do the same thing with the second interval for our second trapezoid. So if I evaluate my function at -2, I should get 6. Let's make sure. Plugging in -2, the opposite of -2 is 2, and 2 plus 4 is 6. Good. So we got base 1 length is 6. The second base length should be our function evaluated at 0, and that should give me 4. So I take my 2 base lengths, 6 plus 4, divide that by 2, and then multiply by the width of 2, so we just get 10. So that's the area of our second trapezoid. Let's do our third trapezoid. Evaluate our function at 0. Well, we already did that. Hopefully we don't have to redo it. We get 4. And then evaluate the function at 2, the right endpoint of our last interval. So if I plug in 2, I get -2 plus 4, that's 2. We can verify that on our graph here. So our base length is 4 and 2, so add those together, divide by 2, and multiply by the width of the trapezoid, and we get 6. So we add up all of those individual areas and get the total area underneath that graph is 30. Notice how we got this same exact approximation. So the midpoint approximation and the trapezoidal approximation with linear functions is actually going to be the same. And we could take a look back at that midpoint approximation. We were including this extra area here, but subtracting that extra area there. And so those canceled out, and we ended up with the exact area. So for linear functions, midpoint, rectangles, and trapezoids will give you the exact area. However, when your function becomes more complicated and the graph becomes much curvier, they lose their exact approximations and they just become close approximations. Midpoint approximations are closer than left and right endpoint rectangles, but trapezoid approximations are even closer than that. And so sometimes questions might be which Riemann sum gives you the closest approximation, or which Riemann sum gives you an over or an under approximation. Lots of variety of questions they might ask you when using Riemann sums. So now we should be able to compare all four methods, the left and right endpoint, midpoints, and trapezoidal approximations, and approximate the area under curves.